Welcome to EDU World Space.
Here we're given quite a bit of information concerning the star Delta Scorpii, which is actually a double star and a variable star. So a fairly complicated system, but we are to find some information about the light from this star, and we'll become familiar with some terms and equations dealing with luminosity and magnitude. So the first thing that we'll do is going back to basics, using the Stefan-Boltzmann law, which is actually a thermodynamic relationship that tells us the amount of power per unit area being emitted by a blackbody. That is equal to sigma, the Stefan-Boltzmann constant, which we have over in our constant area, times temperature to the fourth power. And what we recognize from here is that the power is actually the luminosity of the star. So we'll go ahead and figure out the flux. So the power per unit area is actually the flux emitted at the surface of the star. And that's in watts per meter squared. So the flux is equal to 5.6 times 10 to the minus 8 times 28,000 to the fourth power. And actually, we're looking at the answer to question number E for this problem by doing this. And this is 3.50 times 10 to the 10th watts per meter squared. And I will point out that this is equivalent to the average Poynting vector carried by the electromagnetic wave associated with the light. But this is actually the answer to number E. But once we find that the luminosity is the flux times the area at the surface, area of the surface, times 4 pi r squared. R being the radius of the star. Okay, and putting that together, we get that this star is slightly more luminous, well, quite a bit more luminous, 1.17 times 10 to the 31 watts. Quite a bit more luminous than our own sun. And I do have some numbers on our sun written down, so we have numbers for comparison. The next quantity we want to look at is the bolometric magnitude. A bolometer is a device that measures radiation energy at all wavelengths from a blackbody. So it's not picky about which wavelengths it's picking up. So bolometric magnitude, again, we have not filtered the light. We have not used our eyes just to look at the brightness. We're just asking about this blackbody as a whole. What is its apparent magnitude? And for this, I'll go ahead and use a logarithmic relationship that compares the absolute magnitude of delta Scorpii to our sun. And what matters is the ratio between their actual luminosities. So absolute magnitude comes from luminosity, the actual amount of power being emitted by the star. We do know the absolute and apparent magnitudes, of course. For our sun, we put in its absolute magnitude, and then we use the ratio of the luminosities. And the star has a negative magnitude, absolute magnitude, and that means, yes, it is much more powerful than our sun. So remember that negative means bright, lots of energy if it's absolute magnitude. Once we find the absolute magnitude, we can use the distance modulus as one way to figure out the apparent magnitude. And of course, to do that, we need the distance to delta Scorpii compared to 10 parsecs. And that is information that we have. So here's kind of a hint about how you can use apparent and absolute magnitude of a star in order to actually work backwards and find distance. But that difference between the two magnitudes is known as the distance modulus. It is based on the inverse square law of light. And the distance is 123 parsecs. So we get the apparent magnitude is minus 6.47 plus 5.45. The distance modulus is actually a later question. And this is minus 1.02. Fairly bright star, apparent. The next thing we're asked to find is the flux of this star measured at the Earth. We have found the flux at the surface. We've already found E, so we'll go ahead to F. And for this, there are a couple ways to do it, but I am going to use the logarithmic relationship, that the comparison between two fluxes is equal to 100 times the difference between their magnitudes apparent divided by 5. And what we'll be doing is we will be comparing the sun. So we'll consider the larger quantity. Okay, so these are flux at Earth. And remember, flux is another name for average Poynting vector. Anyway, M2 is going to be basically the apparent magnitude of our sun, very bright. And M1 is going to be the apparent magnitude of delta Scorpii. So the flux from our sun at Earth, so that's important to note, we're really looking at what reaches us. And we take the difference here between the apparent magnitudes. Whoops. And work that out. And that turns out to be 2.11 times 10 to the 10th. Now, we do know the flux from the sun is something called the solar irradiance. And it's equal to 1365 watts per meter squared. So using this ratio, we could calculate, the quantified flux from delta Scorpii would be 1365 divided by 2.11 times 10 to the 10th watts per meter squared. Yeah, we could do that, but the number would be quite small. We'll go ahead and do it anyway. It's about 6.5 times 10 to the minus 8 watts per meter squared. Oh, and finally, just to remind ourselves that the star is radiating very heavily in a particular region of the spectrum. Let's calculate the peak wavelength from this black body. So using Wien's displacement law, peak wavelength times the temperature is 0.002898 meters times Kelvin. And of course, we're going to use 28,000 Kelvin. And we get the peak wavelength equal to 103.5 nanometers, which is ultraviolet.